About this particular problem. This problem, we just use dimensional analysis to try to string it together. We just have to label it properly, like the density. We have to label that properly. So milliliters of sodium hydroxide solution, we just look for something that cancels it. And the only thing that would cancel it is this. We have grams of sodium hydroxide solution. The only thing that would cancel it is this. So just got to make sure that we pay close attention to the units. Then we should be able to solve these problems. It might take time, but as long as, you know, it's like a puzzle. As long as all the puzzle pieces are there with the right units, then there's only one way to string them together. Sometimes there are multiple ways, but they lead to the same answer. Let's look at the next problem, 90. If a solution of silver nitrate is added to a second solution containing chloride, bromide, or iodide, the silver ion in the first solution will precipitate the halide. That's silver chloride, silver bromide, or silver iodide. So chloride, bromides, and iodides, those are halides. We know that chloride, bromides, and iodides like silver ion. All three of these like silver ion. So precipitate out silver chloride, silver bromide, silver iodide. Will all precipitate out. Sometimes precipitates they represent with a down arrow like that. Okay. Halides are just the anions for the halogen. A solution excuse me, a solution contains 0.230 grams of sodium chloride. And 0.771 grams of sodium bromide. How much silver nitrate do we need to add? So in this case, maybe we'll just do grams of silver nitrate. This would be grams of pure silver nitrate. It's probably in solution, but we could add solid silver nitrate to this as well. So how many grams of pure silver nitrate is required to precipitate out both of these? Sometimes what people try to do is they try to combine this all in one equation. So we want the sodium chloride and the sodium bromide to precipitate out with the silver nitrate. So when I look at this, I'm going to need 1 silver for the chloride, 1 silver for the bromide. So that's going to be 2 silver nitrates. This is going to form silver chloride plus silver bromide plus 2 sodium nitrates. Silver chloride's a precipitate, silver bromide's a precipitate, everything else is aqueous. So sometimes, you know, if I got sodium chloride and sodium bromide, they both react with silver nitrate, they try to combine it into one equation, like this. I've seen this, but this is a mistake. What's wrong? There's something seriously wrong with that equation. What is wrong with that equation? Is it balanced? Looks okay, doesn't it? Looks okay, but there's a problem with this equation. If I write an equation like this, the problem is this. It's that we already know what the, what's the question? The question is that what the problem is this. How do I know it's a 1-to-1 ratio of sodium chloride to sodium bromide? It's a 50-50 mix. Is that the case? This is a 50-50 mix of sodium chloride to sodium bromide. It's a 1-to-1 ratio? No. In fact, that ratio can be any ratio I want. It doesn't have to be 1-to-1. It could be like 99% sodium chloride and 1% sodium bromide. There's nothing restricting that ratio. I can mix it unless it's forbidden. Is there any percentage forbidden? Like say 75% is forbidden. You can't mix up a 75. No, you can mix up any percentage you want. And so the serious problem with this is it's being mixed in a 1-to-1 ratio. I don't know if it's a 1-to-1 ratio. And so what I need to do is this. When we don't combine it, we just look at it individually. And so I treat this as two separate problems. I'm going to need some silver nitrate to react with the sodium chloride. And then, as a second problem, I'm going to need more silver nitrate to react with the sodium bromide. And so what we'll do is we'll just do this. First, we'll just take the silver nitrate and react it with the sodium chloride. Here, I know it's got to be 1-to-1 because, however much sodium chloride I have, I need an equal molar amount of silver nitrate. Because this is going to precipitate out my silver chloride and leave me with sodium nitrate. And so here I have 0.230 grams of sodium chloride. So I go from grams of sodium chloride to what? Moles of sodium chloride. From moles of sodium chloride to moles of silver nitrate, and then from moles of silver nitrate to grams of silver nitrate. And so this is the number of grams that are required to precipitate out this amount of sodium chloride stoichiometrically. And then I'm going to do an entirely separate problem with the sodium bromide. So I'll take my silver nitrate and add it to sodium bromide. When I do that, I'm going to get silver bromide precipitate plus sodium nitrate. And so in this case, I have 0.771 grams of sodium bromide. And then just do the same thing. Go to moles of sodium bromide to moles of silver nitrate. From moles of silver nitrate to grams of silver nitrate. And then what I'm going to have to do is I'm going to have to add these two up together. I'll just sum it up to get the total grams. Out of that total, some will be for the silver chloride, some will be for the silver nitrate. So they wrote two separate equations, but they didn't separate them. Wrote an equation for silver nitrate plus sodium chloride, and a second equation for silver nitrate and sodium bromide. There should be a period or something here. Then we went from grams of sodium chloride to moles of sodium chloride, moles of sodium chloride to moles of silver nitrate, moles of silver nitrate to grams of silver nitrate. .669 grams of silver nitrate for the sodium chloride, 1.27 grams for the sodium bromide. We'll just add them together. This is the amount for the sodium chloride, this is the amount for the sodium bromide, so altogether we need 1.94 grams of silver nitrate to react with both. All right, so that's an overview of the type of homework problems you encounter for stoichiometry. We're going to hit stoichiometry again when we get to solutions. We aren't done with stoichiometry, but we're done with chapter 10. And gases also will do stoichiometry, so stoichiometry is going to be the topic. We're going to move on to chapter 11. chapter 11 deals with the theory of chemistry. You know what the theory of chemistry is called? Theory that underlies chemistry? Atomic theory, but you know, it's different than Dalton's atomic theory. The theory that underlies chemistry is called quantum mechanics. Quantum mechanics, or the quantum model, or quantum theory, or quantum chemistry. It's quantum. Quantum is the theory that underlies it. So if we want a deeper description of what's happening chemically, then we should look at quantum. The development of quantum mechanics pretty much followed the scientific method. Well, what are the steps in the scientific method? Observation. Well, let me tell you the observation that led to quantum mechanics. The observation that led to quantum mechanics are the observation of unusual light patterns. These unusual light patterns eventually evolved into quantum mechanics and quantum theory. So the first thing we need to talk about, is light. And what were these unusual light patterns that were observed? When we talk about light, we're talking about electromagnetic radiation. Light is the energy in the form of electric and magnetic waves. Electromagnetic radiation includes gamma rays, X-rays, ultraviolet, visible, infrared, microwaves, and radio waves. The energy is transmitted at the speed of light, that is 3.00 times 10 to the 8 meters per second, or 186,000 miles per hour. We characterize light based on this lambda. Lambda is called the wavelength, and this, nu. Nu is called the frequency. So light's characterized by its wavelength and frequency. The speed of light is the same. So for example, radio waves move at the speed of light. Microwaves move at the speed of light. Visible light moves at the speed of light. In fact, all those move at the same speed, which is the speed of light, which is a constant in a vacuum. What are these waves? These waves are what we call oscillating fields. Oscillating electric and magnetic fields. So let's just concentrate on the magnetic field. An oscillating, not magnetic. Well, let's talk about an oscillating magnetic field first. If you have an oscillating magnetic field, then what happens is it oscillates. So in one instance it's north, the next instance is south, right? North, south, like this. It's coming at you at the speed of light. So let's say something's coming at you at the speed of light and it's moving north, south, like this. So if you're a tiny magnet, what would happen? If you were a tiny magnet, this is what would happen. You'd be okay here, and then in the next cycle, you'd flip. And then you'd flip again, depending on what the wave is like. And so you start flipping like this. If you're a little tiny magnet. But an oscillating electric field is going to look like this. An oscillating electric field, let's say it's moving very fast, 186,000 miles an hour. It's moving very fast at the speed of light. It's called its velocity. 3.00 times 10 to the 8 meters per second, which is c. C is the symbol for the speed of light. This is equal to its velocity. Velocity is v. What we're saying here is this. Now, an oscillating electric field is not north-south. An oscillating electric field is plus, minus, plus, minus, plus, minus, plus, minus. And so, an oscillating electric field would interact with a matter. like this. If you're an atom like that, there's a nucleus in the atom. The nucleus contains all the mass, pretty much all the mass, or nearly all the mass, and the positive charge. And so if you're the nucleus, you're going to see this field coming at you at the speed of light. And what you're going to experience is plus, minus, plus, minus, plus, minus. But the thing about the nucleus is in relative terms, when we get to very small scale, kind of massive. And so the nucleus isn't really perturbed by this wave coming by. However, the electron isn't so massive. The electron is very light. And so as this wave comes by, the electron will interact with the wave. The electron's going to move with the waves. Whereas the nucleus, being kind of massive, doesn't really move. It's kind of stuck. And so what we're interested in is how light, these electromagnetic waves, interact with matter. And how light interacts with matter is a field called spectroscopy. Spectroscopy measures the interaction of light with matter. Now, we have lots of different types of light. Let's take a look at the different types. So we have gamma ray spectroscopy, which uses gamma rays. We have radio wave spectroscopy, which uses radio waves. And so let's just go down the list. Gamma rays, what characterizes gamma rays is gamma rays will have a short lambda. Lambda is wavelength. And the wavelength is a peak-to-peak distance, or trow-to-trow distance. And so the wavelength would be from here to there, would be the wavelength, or from here to here. And when we look at gamma rays, the wavelengths are very small, 10 to the minus 16, 10 to the minus 14, 10 to the minus 12 meters. Now, how big is an atom? An atom is about 10 to the minus 10 meters. So gamma radiation have wavelengths even smaller than an atom. Whereas radio waves have wavelengths from a meter to 100 meters to 10,000 meters to 1,000,000 meters to 100 million meters long. And so huge distances between these. So gamma rays have short wavelengths. If it has short wavelengths, then what happens is this. It's going to be oscillating very fast because this is moving at a constant speed. So if we're here, then it's oscillating plus minus, plus minus, plus minus at an extremely fast rate. How fast? Well, the rate that it oscillates is called the frequency. And the frequency is measured in hertz. A hertz is 1 cycle per second. And so this is going to be high frequency. High frequency gets the symbol nu. This is lambda. Is nu. And mu is the frequency. So it's extreme. These frequencies are extreme. 10 to the 24, 10 to the 22nd, 10 to the 20 hertz. Cycles per second. That is one up-down cycle in a second. It would be 1 hertz. Even radio waves have extremely high frequency. Like AM is in kilohertz, thousands of kilohertz. FM is megahertz. So 1,000,000 cycles pass by in 1 second. It's oscillating very fast. Gamma rays also have the highest energy. So this is going to have the shortest lambda, the highest frequency, and the highest energy. A little bit longer wavelength would be X-rays. X-rays have a little bit longer. wavelength, a little bit lower frequency, and a little bit lower energy. And then UV. UV is what? Ultraviolet. And then we have something called visible light. Visible light is made up of a whole bunch of colors. Visible light is made up of violet, indigo, blue, green, yellow, orange, red. Do you have those memorized? Someone? Well, you know how people memorize it? They memorize it by Roy G. Biv. Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. Roy G. Biv. And so violet is the highest energy visible light, which has the shortest wavelength of visible light and the highest frequency. Red is the lowest energy visible light, the longest wavelength, and the lowest frequency. Visible is called visible because we could see it. Ultraviolet is invisible. X-rays are invisible, gamma rays are invisible. On the other side of red is IR. You know what IR stands for? Infrared. So ultraviolet is on the other side of violet. Ultraviolet. And infrared is on the other side of red. Infrared. Infrared radiation or electromagnetic radiation or light is invisible as well. And then we're going to have microwaves. Like your microwave oven, use microwaves, heat up the food, and then radio and TV waves. TV being even lower frequency. TV would be the long radio waves. And so radio and TV would have the longest lambda, the lowest frequency, nu, and the lowest energy. So let's take a look at radio antennas first. A radio antenna, what were the old radio antennas made of? You know? They used to have these antennas you pull out the hood, and the problem with them is they break. If the antenna breaks, can you use anything? Like say I have a piece of wood. Instead of using the metal antenna, I just use a piece of wood. Would the wood work as a good radio antenna? No. And so what people would do is they get an old metal clothes hanger and jam it in to where the antenna used to be. And it would work okay. It would work okay because metals. Antenna, it's probably not spelling supposed to be good. But if I look at radio antenna, it's metal. One thing about metals are the electrons are loosely held. The electrons are free to move. This is why metals conduct electricity, because electrons are kind of loose, very loosely held. This is why metals are easy to oxidize, because the electrons are loosely held. They aren't so tightly held. And so what happens is a radio wave comes along. Radio wave comes along and it's plus, minus, plus, minus. Well, electrons are minus. And so in one instance, the electrons are repelled, the other instance is attracted. And so what's going to happen is a radio wave comes along, and then the electrons are going to start oscillating with the radio waves. Uh-huh.
Are radio waves dangerous for our health?
Are radio waves, it depends on, like, for example, the radio waves aren't really going to do anything to you, but it depends on how much energy, you know. For example, you know, you could be under an infrared lamp, or we could feel infrared radiation. You can feel infrared radiation, like if you stand in the shade and then you put your arm in the sunlight, you know, when you're standing in the shade, it's cool, but if you stick your arm in the sunlight, it's hot, right? And so it's not the air. A lot of people think it's the air temperature is hot. It's not the air temperature, it's because you're being hit with infrared radiation. And so half your arm could be cool and the other half could be hot just because of the exposure to infrared radiation. Well, I don't worry about putting my hand here, and I don't worry about looking out there. But if instead of just infrared from the sun, it was an infrared laser, then if I did this, if I look at an infrared laser, I would go blind, permanently blind. You have to wear special goggles. When you work with an infrared laser, you got to work with special goggles, because if that infrared laser hits your eyes are burned, basically. And so it depends on how much power you have. And so if you're standing in front of, let's say, a megawatt radio wave emitter, I would worry. You know, I wouldn't stand in front of a huge radio tower, you know. But if you're some distance away, I wouldn't worry about it. Right now, your body is bombarded by a huge number of radio waves. But the situation is that our electrons are pretty tightly held. So if you try to hold on to this to improve the reception, the radio waves, most of the radio waves are just passing right through your body, doing nothing. They're doing nothing because there's nothing to couple with that, basically. And so what radio, in terms of spectroscopy, radio waves have enough power to excite electrons in metals. But they really can't excite electrons in your bone or your flesh or water, because the electrons are more tightly held. They aren't allowed to oscillate with the radio waves. However, if you take that metal and put it into a microwave, what would happen? Have you ever tried to put metal into a microwave? Yeah, what's going to happen is you get sparks, right? You get sparks because the electrons get a little bit too excited. The electrons get too excited, well, because microwaves, radio waves are like this, but microwaves are like this. And so if you're an electron in the metal and you're trying to keep up, and it's too hard to keep up, and then you get knocked off. And so microwaves can knock electrons off metals. The electrons get too excited. And so that's called ionize. When we knock electrons off, we ionize it. And so we can ionize metals, but I wouldn't want to stand in front of a microwave tower. You don't want to stand in front of a microwave tower because it's not because you're made up of electrons in a metal. It's because you have a lot of water molecules in your body. And when we look at water molecules, is there any charge? Are water molecules neutral or charged ions? They're neutral. Water molecules are neutral. However, when we look at it, different regions are not neutral. So for example, when we go by the oxygens are partially negative. They have a little bit of negative charge. We'll call that, this little symbol means delta here. Delta minus means a little bit of negative charge. The hydrogens have a little bit of positive charge, like this. So what happens is the microwaves come along like this, the molecule tries to flip, right? depending on what side it's oriented. So you got a molecule like this, it's trying to flip, so positive, negative, positive, negative, positive. And so what eventually happens is the molecule starts to rotate with it. And so the way microwave ovens work is microwaves have just enough energy to rotate water molecules. As these water molecules rotate, that's going to increase the kinetic energy of the water molecules, thereby heating it up, heating the water up. And so this could rotate. Microwaves are known to rotate small molecules. It takes a bit more energy to, this is called a bond here. The hydrogen and oxygen are bonded together. These atoms are stuck to one another. But if you look at the hydrogen is positive, the oxygen is negative. The positive and negative cancel each other out, so the whole thing's neutral. But when we look at it in detail, the hydrogen is positive, the oxygen is negative. So as infrared radiation comes along, what happens is this bond can vibrate. And so microwaves cause rotations, infrared causes vibrations. A little bit more energy is required for vibrations over rotations. So these atoms start to vibrate as they couple with the field. Visible light, this excites electrons in matter. A lot of matter has color, and that color is a result of these electrons being excited in matter. Ultraviolet has enough light to break bonds. So ultraviolet here, yeah, these atoms start vibrating, but they vibrate too much, too intensely. They vibrate too much, eventually that bond is broken. Ultraviolet causes cancer?
Everything like ultraviolet strawberry can cause cancer.
Yeah. Yeah, everything ultraviolet. What happens is causes cancer, like your DNA. Your DNA has bonds there. On ultraviolet exposure, the DNA will break the bonds in the DNA and cause mutations and cause the cancer.
And where would Wi-Fi rays be located?
Wi-Fi rays are down here at the microwave level. And so microwaves operate at about 5 gigahertz, microwave ovens. And so your Wi-Fi is either 2 or 5 gigahertz, so it's in the microwave region. Yeah, bond breakage is bad. X-rays have a little bit more energy. X-rays will excite electrons in matter to the point where they get knocked off. And so X-rays and gamma rays are what we call ionizing radiation. Ionizing radiation, because they'll ionize most matter. That is, excite the electrons so much that the electrons get knocked off the atoms, molecules. This is a water wave. A water wave is not the same thing, electromagnetic wave. This is just showing the wavelength, lambda. This is visible light. The visible light, one of the biggest sources of visible light is the sun. But when we look at the light coming off the sun, it's white light. White light is all the colors of the rainbow put together. And so the way we can see that is if we pass the white light through some slits and then through a prism. And then what we can do is we can separate out the white light into its component colors. You recall the colors? Let's start off with red. We would go red, orange, yellow, green, blue, indigo, violet. So Roy G. Biv. Red being the lowest energy, violet being the highest energy. Red being the longest wavelength, violet being the shortest. Red being the lowest frequency, violet being the highest frequency. Yeah. So, what's the biggest source of white light? The biggest source of white light is the sun. You know, the sun is a gigantic light bulb, basically. Gigantic light bulb. So how does the sun work? We know the sun gives off all the colors. It gives off, not only does the sun give off visible light, but the sun also gives off infrared and ultraviolet. Hopefully not too much X-ray and gamma ray, but I guess they're bursts of X-rays and gamma rays. And radio waves, there are radio waves that are emitted from the sun as well. But we'll just focus on these. Now, how does the sun produce this visible light? You know how the sun produces light? Well, what is light? Light is the transmission of energy by these electromagnetic waves. And the sun is a giant fusion reactor, a nuclear reactor producing it. There's a lot of energy produced. What is the sun made out of? Yeah, it's made out of a gas. What gas?
Hydrogen.
Hydrogen. The sun is mostly made up of hydrogen gas. But we don't even, it's really, the sun is not just a gas. Really, maybe we should call it a plasma.
Oh, yeah.
Now, what is a plasma? It's what happens, you know, it's a combination of gas and plasma. And so this is what happens. What happens is if you take a solid and heat it up, you add energy, you're going to form a liquid. If you take a liquid and add energy, you form a gas. And if you take a gas and add energy, you form a plasma. And so plasma is a high energy gas. That's all it is. What happens in a high energy gas? In a high energy gas, there are high energy collisions. And so the hydrogen in the sun, is it H2? Or H? Yeah. The hydrogen in the sun, well, there are no molecules that exist. There's too much energy. There's too much energy because if there were molecules, what would happen is they collide with one another. They collide with so much energy that the bonds break. We don't even need UV for this. And we get two H atoms. And then what happens is these collisions happen, and then the hydrogens have electrons. And those electrons get excited. And so what will happen is that if I add more energy to this, I'll have excited hydrogen atoms. Excited hydrogen atoms, the electrons are very excited in the atom. In fact, the electrons can get so excited that they get knocked off the atoms, and we form hydrogen ions. And so they're hydrogen ions in the sun, in free electrons. We call them free electrons. What happens is these free electrons can get excited too. And so what we'll see is the electrons can have different energies. And so if we make a plot of energy on the y, the electrons can get excited, but they don't stay excited forever. Eventually they'll drop down. When they drop down, they'll emit radiation. And so we can excite the electrons to higher energies up here, and they drop down, and eventually they'll form a whole rainbow of colors, a whole rainbow, like red, orange, yellow, also infrared as well, and UV, you know, yellow, Roy G bid, and then we go to UV. And so these electrons can get excited to higher and higher energies. But the first law of thermodynamics says this. The first law of thermodynamics says energy is neither created nor destroyed. So if the electrons get pumped up in energy here, they're going to drop down. And as they drop down, they emit that energy in the form of light, radiation. So that's what's happening there. So we can make a light bulb. You know, when the sun is on the other side of the earth, then we need to make a light bulb. How do you make a light bulb? Do you know how light bulbs operate? We can make light bulbs like this. These are the old-fashioned light bulbs. These are the incandescent light bulb. In the incandescent light bulb, we have a metal. They use tungsten metal. You know why tungsten metal is used? Tungsten metal is used because it has a very high melting point. Tungsten metal is hard to melt. Take a look at where tungsten is located. What's the symbol for tungsten? W. So tungsten's next to rhenium, osmium, iridium, platinum. All these metals are extremely dense and have a very high melting point. That's important. Because what we're going to do is we're going to excite the electrons in tungsten metal. And so if I have some tungsten metal here, the electrons are loosely held. The electrons are kind of loosely held in metal. And so what we'll do is we'll excite the electrons. Well, there are different ways we can excite the electrons in tungsten metal. One of the ways we can excite the electron is to pass an electric current through this. If we pass an electric current through this, there's some resistance and things start to get hot. And the metal is going to start to get hot and the electrons will start to get hot. So have you ever held a piece of metal in a flame? You know, initially it's going to get hot, but the color doesn't really change. You can feel the infrared radiation coming off it, a hot piece of metal. You know, before you touch it, you want to feel if you can feel any infrared. I don't feel any infrared coming off here. Really okay. But eventually it'll start to glow. You've seen the metal glow? I don't have any matches. I forgot to get matches earlier. But you might see it glow red hot. Have you seen metal glow red hot like this?
Yeah.
Yeah. Before it glows, now it's emitting, not only is it emitting infrared, but it's also emitting red. Maybe some orange there. And so as that piece of metal gets hotter and hotter, then it'll start emitting orange yellow, and eventually it'll start emitting white light. If it doesn't melt, you know. And so tungsten won't melt. It'll get so hot, it'll start to glow white hot. And white hot, that's all the colors of the rainbow. And so that's all we need. But the situation with tungsten is it's prone to oxidation. And so oxidation is a problem because as that tungsten gets hot, and if there's any oxygen around, that oxygen will oxidize the tungsten to form tungsten oxide, which is going to be very brittle and it's going to crumble. And so when we look at a light bulb, like this, to prevent oxidation, do you know what they do? They seal it in an oxygen-free atmosphere. And so the gas inside the light bulb contains no oxygen. If oxygen got in here, it's going to oxidize this tungsten immediately. gonna break. And so we have to have some other gas in here, and gas, oxygen-free gas. Sometimes they'll put halogens, like chlorine and bromine here, because sometimes the tungsten atoms vaporize off the surface here. If it gets so hot, the tungsten atoms vaporize and deposit on the inside, start to darken from the inside of this. To prevent that from happening, they put some halogens in there, which eats up the metals deposited on the inside surface here. Deposits them. Well, what's happening here are the electrons. The electrons are getting excited. In fact, the electrons are getting excited to many different energies. And what's being emitted is what we call a continuous spectrum of colors. So here, this would be the continuous spectrum. The sunlight emits a continuous spectrum of colors like this. And that's just coming from excited electrons. And so what we can do is we can try to make a light bulb out of hydrogen, just like the sun. We'll call it the hydrogen lamp. The hydrogen lamp. Now, making a light bulb out of gas is a little bit more tricky. You know, typically when we make a light bulb out of gas, we gotta worry. I mean, you've seen we can make a light bulb out of air. Light bulb. Except this doesn't look so good, does it? I mean, if you were to have like sparks going across, then the light wouldn't stay consistent. That's because of the there's a lot of air and there's a lot of collisions there. And so rather than doing that, this is how we're going to make the light bulb out of hydrogen gas. Here. We're going to put a low pressure hydrogen gas in the tube. And then we're going to have a little lightning bulb here. This is a controlled lightning bulb because of the low pressure. If this were high pressure, then this would be jagged and all over the place. But since it's low pressure, we get a nice little lightning bolt here. And so what's happening here is, this is what we call an electric discharge in hydrogen gas. We're exciting the hydrogen atoms. Now what do hydrogen atoms consist of? Well, if there are any molecules in those, the molecules break apart into atoms. And so if I have a hydrogen atom consists of a proton and an electron. You know, the most abundant isotope is one proton, one electron. And then what we're going to do is we're going to excite that electron using electric discharge. So we should be able to excite that electron to any energy. So for example, if we excite it to low energy, it should start emitting infrared. A little higher energy, it might start emitting red, and then orange, yellow, green, blue, indigo, violet. But we don't want to excite it too much, because if we excite it too much, what will it start to emit after violet? Ultraviolet. And so we don't want too much ultraviolet. Some people do because they want black lights or whatever, but they want the tan. But we don't want any eye damage, so we'll try to minimize the amount of ultraviolet by not exciting the electrons too much. So basically, we should be able to excite the electron to any level here, as long as, you know, like in that lightning bolt. A lot of air atoms, we can excite those. A lot of hydrogen atoms, we should be able to excite them. Some a little bit, some a lot more. And so this is what was predicted. This electron here should be excitable, and we should be able to excite it to any energy we want. And so what was predicted by physics is we should see a continuous rainbow of colors from a hydrogen lamp, just like from the sun. Continuous rainbow of colors. But what was observed is not a continuous rainbow